Hi everyone, we are into chapter 3, and what we're going to be doing in this chapter is moving from the ancient world into the modern world. And we have a lot to go through, and it's all in developing the scientific revolution and the scientific method. So let's get started. What we're going to cover in this chapter is astronomy before Copernicus. So we're going to come out of Greece and move into Western Europe by the end of this. We're going to cover Copernicus, Brahe, Kepler, Galileo, and Newton. So we have a lot of ground to cover, and I think you're going to be amazed by the genius of some of these people and the way they thought in such a countercultural way. So let's start with what we knew before. The Greeks were developing scientific models. They developed the first model that the Earth was at the center of the universe. And just to remind you, a scientific model is a visualization of a phenomena. So I thought you'd like this over here about black holes. It's a visualization of a phenomena, black holes. And a lot of what we are studying when we get into Newton directly impacts black hole work now. So his work back in the 1660s directly impacts Einstein and directly impacts the black hole that we may have just found like 2 weeks ago. So it's really very current. When we think about a scientific model and its place in the scientific method, it is right near a hypothesis. So if you come up with a prediction about a phenomena, then you make a visualization, because like I told you, every scientist who's a good scientist starts out by sketching, and they sketch everything before they write it all down or before they start anything. Just review, to go back, we were talking about the zodiac when we last left chapter 2, and the Babylonians. We were about 500 BC there. And over in Greece, just across the way, there was talk about spheres and the fact that there was a celestial sphere, and that this was a well-known universal, independently universal realization that the stars had to be in a sphere over the earth. The Greeks took it a little bit farther, and they said that this sphere is more of a philosophical bend to it, and they looked at spheres as perfection. Now, the sphere model that we're talking about in 500 BC actually didn't make a whole lot of sense. And it didn't make a whole lot of sense because it had the Earth in the middle, of course, and it had the stars, which are very small, as being closest to the Earth, which makes no sense because the moon is much bigger and the sun is much bigger than anything. So why wouldn't the sun be closest and the stars be farthest? Not making a whole lot of sense there. But this was all led by Plato back around 400 BC, and he develops this big philosophical bend that that astronomy compels the soul to look upwards and lead us from this world to another world. It's kind of religious there, kind of blending philosophy and religion and science. And his thing was that the sphere is a perfect shape. It moves in a perfect circle. It stays at a constant speed. This represents harmony. Okay, and this is Plato here, and this is his star student, Aristotle. And when Aristotle was learning from Plato, Aristotle learned that Plato had developed a universe of 27 nested spheres. Okay, that's your first hint that this isn't going to work. because the best science is elegant and logical, and basically you can draw it on a napkin. If it's more complicated than something that you can draw on a napkin, you probably have something wrong there. His philosophy was known as uniform circular motion. We taught it to Aristotle. Now, Aristotle took that a little bit farther. And after Plato died, Aristotle said, well, the earth isn't perfection. And the earth does have a lot of imperfections, and it could be corrupted. And there's no reason that I need to explain this to you, because my philosophy is that truth is based on first principles. And first principles are so obviously true that they need no examination or explanation. So that's your second hint that this isn't going to work. Because science and defensiveness do not go together. It sounds autocratic. It sounds insecure. That's not what science is. Aristotle, went full tilt. He went to 55 nested spheres because by that time they were noticing more what they called wanderers. And they called them planets for the Greek word for wandering. And we'll get into that in a second. And they noticed more stars, so they had to have more spheres. This was a geocentric philosophy, that the earth ruled the heavens. This philosophy lasted for about 2,000 years. Now, why are you always insisting that the earth is in the center? And that's my dog coming in through the door back there. My dog thinks she's the center of the world. Anyway, why are you insisting that the earth is in the center? Well, at this point, mathematics was starting to become a very big deal, and especially geometry. And triangulation and Pythagoras, who was Greek, was all the rage. So you know about triangulation, and you know about taking an angle at one point, A, and taking an angle at another point, B, and measuring the distance between them. And by doing that, you can calculate the distance to the tree. At this same time, another mathematician in Greece, Aristarchus, took this same emphasis on geometry and flipped everything on his head and came up with another model that was sun-censored, that the sun was at the center of the universe. This was right around the time of Plato and Aristotle, and he presented his work in Greek and was roundly rejected by Plato and Aristotle and the Academy. His work was never appreciated and was rejected outright and lost for hundreds of years. So 2,400 years ago, somebody had it right. Why would Aristotle insist that Earth was at the center of the universe? It had to do with a technique for measuring distance in space called parallax. And parallax is triangulation for the universe. It is using the same angles and distance that you would use on Earth to measure distances in space. It's still used today to measure distances in space as a geometrical measure. There is an interesting and fascinating apparent effect with parallax that is so compelling that the Greeks really went full tilt with it, and it started to direct their thought patterns. Let's talk about that a bit. with parallax and this particular technique, there is an apparent effect which apparently, but not really, moves things that are close to the origin. For instance, if you hold your thumb very near to your eyes and you close one eye and close the other eye, your thumb appears to move. The object is the thumb, and it is close to your origin, which is your eye, and your eye has two different distances, A and B. If you move your thumb farther out, and then you close one eye and close the other, your thumb doesn't move nearly as much. This is an apparent effect. It is not a scientific effect. And the Greeks took this to say that bright stars should be closer and dim stars should be farther away. No data behind this, and there was no way they could collect data for this, but they assumed it. So, if we can measure the distance to the close stars, the close bright stars, then we should also be noticing that they are moving relative to all of the distant stars. And so they started to measure the distance to their bright stars. And then they started to notice that their bright stars were not moving relative to their distant stars. Now, just a sideline here, this little trick of apparent movement is so compelling that in Apollo 13, the scene where Tom Hanks gets a little drunk at the party before he leaves, and he goes outside and sits out and plays with the moon in his thumb, is a scene about parallax. So we still use this in modern days. When the Greeks could not find the close stars moving relative to the distant stars, they were perplexed because their hypothesis was that those close stars should move relative to the distant stars. When they didn't, they said, holy cow, that's not the way it's supposed to be. And so that I guess the Earth is not moving when we see the seasons change in the zodiac. Because if we saw the seasons change in the distant stars with the zodiac, we would have seen the closer stars move differently. And they didn't. So therefore, the Earth must not move. And that's kind of crazy, but that lasted for 1,600 years, that entire framework. And in fact, stellar parallax does work, but it only works when you have very, very close calculations made by very accurate telescopes, and those were not available until the 1700s. So this lasted a long time, and we are going to come back to this soon.